All right, good afternoon again to everybody. I'm Billy Boshoff from the University of Pretoria. I'm a director of the Concrete Society of Southern Africa, and it's my pleasure to welcome you, as the screen says, a warm welcome to everybody here today. We've got an interesting presentation today. We've got two presenters, two ladies, both PhDs, and they will be speaking more about not concrete technology, but more on the side of concrete mechanics and structural engineering, which is very interesting. I'm just going to go through a short slide, a few slides, just a few things about the Concrete Society, and then I'll make as quick as possible, and then we'll get straight on to the presentation, what you actually came here for. So firstly, at the Concrete Society, we've got three core values. We remind ourselves the whole time about it, remind our members and possible members. We're all interested in being modern and advanced, relevant, streamlined and efficient, objective, inclusive, and loyal. We've got a few committees going. I'm not going to go into the history of the society now, but we closed our doors for a few years and we opened now for 6.5 months, I think, or almost 7 months. And we've already got the Inland Branch Committee going, a KwaZulu-Natal Branch Committee, a Western Cape Branch Committee, a Ready Mix Concrete Committee, which I'm the chair of, a FIB Committee, which I'll talk a little bit later about. Just before I introduce the presenter, but the head of delegation is Dr. Sarah Skorpen, which is also the presenter today, one of the presenters. And we've got a cement branch committee, and chairperson there is Mark Hoving. Just our membership, why do you become member? One reason is these webinars we present twice a month. It's free. It is for everybody in the whole wide world can log on and RSVP and join us. But if you want CPD points for it, you have to become a member, unfortunately. But it's a fortunate thing to be a member, be part of the family of the Concrete Society. And we can, it's only possible to do all these presentations if we have members. We need members. And the members need the Concrete Society, as you would say. So to become a member, individual member is only 1,500 Rand per person per year. And then you can become members as a company, like a Emerging Enterprise, Tanzanite, Emerald, Ruby, and Diamond at different prices. And then you can nominate the members to join. And you will also get exposure at events like today as well. You'll be mentioned if you're a company member, which I'll do the next slide. Academic memberships are subsidized, and we also have associate memberships, but more about that in the next slides. We've got diamond members, CRISO and Quick Group. If you were a diamond member, your logo would have been shown up here as well. Emerald member, CTS Laboratories, Corestruct, SNA. Tanzanite members, I'm not going to mention each of them individually, but these guys or these people are Tanzanite members. And these are also a list of more Tanzanite members. And Emerging Enterprise member we've got as well. And then our associate members. And then academic members. I want to thank all our members for joining. Please, if you're not a member yet, consider joining, be part of the family. We all do everything, as we always say, out of the love for concrete. Then upcoming event, Fulton Awards, the big Fulton Awards. Even if you're not a member, you've probably heard about the Fulton Awards. It's going to be Saturday, 7th of June on the Country Club Johannesburg and Woodmead. There's sponsorship opportunities, there are tables, there are individual places you can book to join us. Come join us for a wonderful evening. It's going to be, as always, bigger and better than in the past. Sponsorship opportunities. I just mentioned that. It's just the next slide showing about sponsorship opportunities. And you can just go to the Concrete Society website if you want to know more about the opportunities. Then we've got this CONCRETEfix and concrete class webinars. Like you will, today is a CONCRETEfix. It's you're getting your monthly fix about concrete, anything about concrete technology, structure, mechanics, all of that. We've got the next one coming up is ultra durable repair and rehabilitation by using crystalline technology by Johan van Wyk and Skorpen. And then there's one going to be in May, 22nd of May, presented by Dr. Rod Rankin. And the 19th of June, Kim Tim from Stellenbosch University will be talking about 3D printing concrete or 3D concrete printing. And the CONCRETEfix in July will be Prof. Mark Alexander, and this topic will still be defined. The concrete class is the other series we've got. That is more about the basics of concrete. That's as if you're going back to university to learn more about concrete. It's been up to now pretty much concrete technology, but we're going to start introducing concrete, structural concrete as well as concrete classes. We can look again at the basics, shear design, whatever, punching design, whatever topic we come up with. And if you suggest a topic we must speak about, please email us, email Natasha, and we'll talk about that. So the next one is Aggregates and Concrete Appreciation of the Role by Prof. Mark Alexander. That will be the 10th of April at 3 o'clock the afternoon. Will be very interesting. And then the May, it will be Janina Kanji from the University of Witwatersrand about alkali silicate reaction. July, we will still confirm the presenter. In August, it will be Prof. Rian Kombrink from Stellenbosch University about supplementary cementitious materials. So there's, for now, yes. There's also the in the Western Cape branch, there's a Careers in Concrete Day. If you're in the Western Cape, it's really useful to join up with them, with the Western Cape branch, about what they do in the Careers in Concrete Day. They're doing it at CPUT premises. And CPD points, as I mentioned already, if you're a member, you get 0.1 CPD point for this event. If you attend all our webinars 2 a month, and we aim to have for 10 months in a year to have webinars, that's 2 CPD points you get for, if you're just an individual member, 1,500 Rand, which I think is not bad at all. You will get the email afterwards with your CPD points, and that will be loaded on our website, or you can just go look at our website and you will see what your CPD number is, or your CPD point number, etc. So also just go to our website if you want to know anything more about the Concrete Society and what we do and how we do it. We're also on LinkedIn, quite active. Follow us on LinkedIn. And the success of the society is thanks to the members and the contributors and everybody attending these lectures or presentations. Thank you very much. I really appreciate that. Or we really appreciate that. Then just the last thing I want to talk about before I introduce the presenters, and that is FIB. You might have heard about FIB, but it's the International Federation of Concrete. It's a non-profit organization. It's got 42 national member groups, meaning 42 countries officially members, approximately 2,500 corporate and individual members, and there's more than 1,000 countries participating in one way or another. The mission of the FIB is to develop an international level of the study of scientific and practical matters capable of advancing the technical, economic, aesthetical, environmental performance of concrete construction. It's a mouthful, but the FIB creates a model code every 10 years. The model code 2020 is out recently. This model code is the forerunner of the new Eurocode. And the Eurocode is often the forerunner of the South African codes. So we're trying to catch up still. But what I'm trying to say is that these guys in the FIB really try and develop the newest and the best model codes available with research available to them. And we have become a member of them, and we're proud to be a national member group of them. So it's not just them anymore, but it's we. And we've got Dr. Sarah Skorpen as the head of our delegation. We're still looking for people that wants to become more involved, even help sponsor the membership fee, which is quite significant, but we'll find a way of paying it. But if you want to become more involved in this FIB, contact me or Sarah or Natasha, and we'll put you in contact with Sarah, and then she will guide you further. So that was a lot said. We can now move on to why we actually here today. We're here for a presentation called The Influence of Concrete Material Properties on Integral Bridge Design. We've got two very, very good presenters. We've got Dr. Sarah Skorpen, who joined the Structures Division of the University of Pretoria in 2011 after 9 years in practice. And she's also the project leader of the SANRAL Integral Bridge Research Team. Then we've got Dr. Megan Brink, completed a PhD in 2024 on thermal effects of concrete properties and is currently running the concrete laboratory at the University of Pretoria. She's done a significant amount of testing of concrete made from different aggregates, just to give some background to what she's going to speak about. So thank you very much, Sarah and Megan, for taking the time to make a presentation and sharing it with us. I know it takes a lot of time. And I would like to invite you to share your screen. I'm going to unshare my screen. Oh, I don't have to. You did it for me. Thank you very much. And yes, and I would like, they're going to alternate between them in the presentation. So I'm not introducing just the one and then the other. So I'm going to leave it up to them, and then I will facilitate any questions we might have at the end. So thank you. We look forward to your presentation.
Thank you for the introduction, Billy. As Billy said, I'm Sarah Skorpen. I'll start the presentation off, and then Megan, my colleague, will basically conclude. So yes, our topic today is the influence of concrete material properties on integral bridge design. And it's something we've been looking at the University of Pretoria for the last about 10 years. So the first question is obviously, if you're not familiar with integral bridges, what is an integral bridge? It's basically a bridge where the deck is tied into the abutment, as opposed to a conventional jointed bridge where you've got a bearing and an expansion joint that's allowing movement, which is typically mostly from temperature changes in the deck, and also obviously shrinkage would also influence that. So the big difference here is that when you've got an effective temperature increase, the integral bridge the deck is going to force the abutment into the fill, and then when you've got a decrease in that effective temperature, it's going to pull it away from the fill. So you can think that obviously the deck length is going to influence how much force is going to be applied here, as well as the deck concrete properties, specifically the coefficient of thermal expansion, the E value, and drying shrinkage. Obviously, the bridge environment is also going to play a role, but in terms of you can't govern the bridge environment, but the concrete properties obviously is something that one can look at in terms of the design. So yeah, this is the big difference between integral bridges and conventional bridges. And a lot of road authorities, SANRAL, specifically eThekwini municipality as well, are really wanting to motivate for more integral bridges, because you can appreciate that they have less maintenance associated with them if you don't have an expansion joint or a bearing. So that's really would be a big benefit in terms of why you would go with an integral bridge. Sorry, just trying to change slides here. Don't know why it won't let me. Oh, there we go. Where we kind of started looking at integral bridges was 2015 with the instrumentation of the Van Zyl Bridge, which was at that point the longest fully integral bridge in the country, 90 meters long. And we were able, together with SANRAL, to put a lot of instrumentation into this bridge to measure strain, to measure temperature, to measure earth pressure, to measure tilt and the movement of the abutments. And we've been logging this bridge since 2015. So we've got a lot of data on it so far, and various people have been looking at this and analyzing this data. And part of our research, our SANRAL Integral Bridge research team, we've been looking into this data in more detail. Here's just an overview of the bridge, just with the length and kind of where we've put the sensors. And we've got a lot of strain sensors midspan and over the supports, and we're measuring temperature there as well. Just to show you a little bit of what the sensors look like. On the bottom left-hand side, that's something called a shape array, which is a string of tilt meters that we put in the abutment, in the center of the abutment, right down to the bottom of the pile to measure the movement of the abutment. So that's kind of showing what's happening there in that abutment. Both of abutment A and abutment F, we've got the shape array. The middle photo is just showing what a vibrating wire strain gauge looks like. You can see it looks like a little dumbbell over there, and that's measuring strain and temperature, so that you can take out the temperature component of your strain. And then on the right-hand side here, we've got an earth pressure cell, and we've got 10 of those behind each of the abutments, so we can measure earth pressure. As part of the project, we also looked at concrete material properties. Obviously, that's the focus of today's discussion and talk. When you are designing a bridge, you're obviously specifying your concrete design parameters. This bridge was designed as a W40 concrete durability mix. And for that, the E value assumed would have been 31 gigapascals. Your coefficient of thermal expansion per TMH7 is 12 times 10 to the minus 6 per degree Celsius. And depending on the thickness of the section, the thicker part of the section would have had a concrete shrinkage factor of 165 times 10 to the minus 6. The measured properties here for the specified, the mixed design concrete, which was with dolerite aggregate and a CEM2 cement, gave us 60 MPa at the 28-day cubes for cube strength, split cylinder of 3.6 MPa, a higher E value of 37 gigapascals. And here our coefficient of thermal expansion was, it's something difficult to measure, and we'll talk a bit about that later, but between 8.5 and 9.5. And then also something that's also difficult to measure is drying shrinkage. And we've tried to do that various ways, but depending on the thickness of the sample, we got between 100 and 300. Obviously, this is a smaller sample, but on the structure, let's call it 100 and 200 times 10 to the minus 6. On the right-hand side here, just a graph that I've shown on a number of presentations, just showing heat of hydration. The bridge deck is this twin spine beam deck, which has been used on a number of bridges. But the thing that was really interesting while they were casting the deck and we monitored the concrete as it was setting, was to see this big difference in temperature between the center of the spine beam and the flange over here. So it was something that really was evident and was seen in all the casts. So yeah, something to be aware of in terms of heat of hydration when you've got differing thicknesses in the deck profile. As I said, drying shrinkage is something in real structures that's difficult to measure, and especially in an integral bridge, if you're measuring strain, you're just measuring one strain value, and it's obviously comprised of thermal strain and shrinkage strain and mechanical strain. So you kind of have to decouple your strains. So to get a drying shrinkage strain for the deck, we actually cast some reference samples over here. On the right-hand side, we've got a thick portion of concrete and a thin portion of concrete there, representing the thin 250 flange and the thick 1 meter beam. So that was one way we did it. And then we also cast some reference cylinders, a 250 diameter cylinder, so a non-standard cylinder. And in all of these samples, we cast this vibrating wire gauge over here, and obviously have been logging that, and we can take out the temperature component and look at what the strain would be. And the strain in these samples is only due to shrinkage. There's no other load on them. So you can see here for the 1 meter thick blocks, the kind of strain, shrinkage, drying shrinkage strain, we're getting up to about 100 microstrain. And then for the thinner panels, it's a bit more than double that. And then for these cylinders, obviously, quite a bit more. Some of these dips here, it was quite interesting, were actually when they had a lot of flooding on site, and you can see what the obviously high humidity and a lot of moisture in the air is doing to the drying shrinkage there. And if we go back to the deck now, just thinking about the effect of the environment on an integral bridge, we've been monitoring temperature over the last 8 or 9 years and have calculated an effective bridge temperature, which is a weighted average temperature of the entire deck here. And that's what's going to push the deck in and pull it out. And summer, winter, the season changes. You can see very consistent, kind of ranging 32 degrees in a season, which is quite a bit less than the range that you're required to design for in CMH7. So you can see very repeatable, and definitely significantly less than actually what you are required to design for. And that is obviously now causing the deck to push into the fill and pull away from the fill. And you can see over a few seasons, this is the curvature in that abutment, pushing into the fill during summer and pulling away from the fill during winter. And you can see pretty much a total displacement seasonally.
Sarah, I'm not sure if you can hear me. I think your microphone went on mute. I don't know how that happened. Can you hear me, Sarah?
Thank you. Yes, I'm
Yes,
back.
all right.
Sorry, I also don't know how that happened.
Okay.
Thank you. Is my screen still showing there?
Yes, it's still showing. It's
Cool.
perfect.
Thanks, Billy. Yes, so I'm not sure where I got cut off, but about 10 millimeters seasonal displacement that we're seeing at one abutment end. That's obviously now causing earth pressure to change seasonally, and you can see here the earth pressure slightly different in the center as opposed to the side, but very consistent. We were only seeing kind of an increase in the pressure in the first kind of 2 seasons, and then it kind of quite stable. But definitely you can see that it's coming down to very low pressures in winter. And here's just kind of comparing the earth pressure in summer, where the abutment is pushing into the fill. You can see kind of getting pressures above soil at rest, and then in winter this is coming right down to very low pressures, and we almost want to recommend basically you should be designing for an envelope of pressure when you're looking at the integral bridge design. So that's just kind of giving a bit of background in terms of what's happening in an integral bridge that is different from a normal jointed bridge. But to go to the real topic of today, which is looking at concrete properties now. If we're saying that the deck change in length is causing change in earth pressure and change in load effect in the structure, if we just look at a seasonal increase of 20 degrees, an increase of 20 degrees and the effect of that on the left-hand side here, abutment movement, on the right-hand side here, the abutment moment at the top here. And we look at what would happen if we had a different thermal expansion. So we've taken it kind of two extremes. We've looked at 6, 9, and 12, and then we've looked at 3 different E values for the concrete. You can see here that expansion of the deck, and negative is expansion on this axis, that expansion of the deck is basically linked only to thermal expansion coefficient. It's not going to be influenced very much by the E value of the concrete, as opposed to when you look at that bending moment that you have to design the deck abutment connection for. You can see that the worst case is always going to be when you've got a high thermal expansion coefficient and a high E value, which is stiffness attracting moment there. And if you obviously had a low E value and a low coefficient of thermal expansion, you would be on the lower end here. So we can definitely see obviously this is for a specific length of bridge. This is on a 90-meter length of bridge, similar to the Van Zyl, but definitely the concrete material properties can have a significant influence on the load effects in your structure. And obviously you can see now the similar but opposite behavior in terms of a decrease in temperature. Now here it's for 28 degrees. Again, that alpha value being really what's governing the change in length of the bridge. E value doesn't have a big influence there. But when you look at the bending moment now, both E value and alpha, the higher that is, the higher the moment that you have to be designing for. Now, if we look at currently our mixed design form and what we're looking at in terms of the concrete mixed design, on bridges, you're using the D2 form, which is basically looking at aggregate type and grading. It's looking at the shrinkage as per SANS 5836, which Megan will talk a little bit about now. And you basically are looking at a 3 and 28 compressive strength and your durability indices. There is no testing or no place for looking at E value and alpha. But when we're looking at integral bridge design, we see these properties and shrinkage playing a role and affecting the load effects in the bridge. So on that note, I'm going to hand over to Megan and she'll carry on and talk about concrete properties.
Thank you, Sarah. So as Sarah mentioned, I will be going through the importance of all the different material properties, especially when looking at integral bridge design. So our current design parameter uses a performance-based approach, and it typically only specifies a 28-day characteristic strength. So the question we need to ask is, how can we correlate this 28-day water-cured strength to actual structures, and how relevant is this? So the concrete properties are important when considering structural analysis and design, as well as for quality control purposes. And therefore, the specifications and testing of the relevant concrete properties is required, such as the characteristic strength, which we are currently specifying. But long-term strength, modulus of elasticity, concrete coefficient, or thermal expansion, and the drying, shrinkage, and creep is also important. So South Africa has a wide range of different aggregates that can be used in concrete. An aggregate type has a significant influence on the concrete properties such as stiffness, the coefficient of thermal expansion, shrinkage, and creep. And it's therefore important to acknowledge that we cannot just assume standard values for these parameters. So this study looked at 6 different aggregate types that were based on locality and the type. And 2 sources were chosen from Gauteng area, which included the andesite and the dolomite, felsite from Mpumalanga. Then we've got tillite and dolerite from KwaZulu-Natal and granite from the Western Cape. The concrete mix design used for the mixtures contain different aggregate types, as indicated in the first table. The water cement ratio of 0.5 was used, and a coarse to total aggregate ratio of 0.45. Additional mixtures using fly ash blended cements as a SEM 2, a SEM 2A and B, and then a SEM 4 were also considered as indicated in the second table, and the aggregate used in these mixtures were dolomite. The mixtures were not designed for similar workability, but rather for constant water content. So considering the strength development for the different mixtures, it is evident that the aggregate type has an insignificant effect on the compressive strength up to 42 days. But it is, however, important to look past 42 days as well. And then for these mixtures, it will typically be a characteristic cube strength of approximately 50 MPa, which is currently the only specified criteria for any design project. Okay, looking at the blended cements, we considered the strength development up to 200 days, and you can see that after 90 days, we've got similar strength of approximately 60 MPa for the CEM1, CEM2A and B mixtures. And to only consider 28-day cube strength when blended cements are used is not necessary if considering that most large construction sites would not be operational after 28 days after casting. So it is important to look at long-term strength properties of concrete that's properly cured. It is also beneficial in large construction projects where you want low heat of hydration to rather use blended cements than pure Portland cement. Okay, considering the E value, unlike the compressive strength, aggregate type has a significant influence on the stiffness of concrete. So the E value for the concrete mixtures ranged between 28 and 39 GPa, depending on the aggregate type used. And the design parameter in the TMH7 specify E value in the range of 28 to 40 GPa for a 50 MPa concrete mix. So the average of this range sits at 34 GPa as indicated in the TMH7. And all the experimental results from the different aggregate types fall well within this range. So it would, however, be better to rather consider a specific E value in design purposes, as Sarah has shown previously. Furthermore, there is no current South African standard to measure modulus of elasticity, and the specimen size as well as the specimen shape will influence these results quite significantly. So concrete compressive strength for less than approximately 60 MPa is normally considered as conventional concrete or normal concrete strength. However, the range of compressive strengths range from 35 to 85 MPa. And then also an additional mixture of 150 MPa is shown in this graph just to indicate the importance of these prediction models. So the relationship derived from Alexander and Mendes in 2005 is only valid up to, between 20 and 70 characteristic strength. And then the SAN standard is only valid for 20 to 60 MPa characteristic strength. So that's why these two is not plotted beyond that. But the general trend indicates that concrete with reduced strength produce lower modulus of elasticity values as expected. However, the increase in modulus of elasticity seems to plateau at around compressive strengths of plus minus 65 MPa. So it would be ineffective to design for lower E values than what the concrete actually is. And we are currently adopting the EN1992. And from the data, it shows that it is a better prediction model to use in design than the current SAN standard. Okay, considering the concrete coefficient of thermal expansion, or the alpha values, the design requirement in the TMH7 specifies a coefficient of thermal expansion of 12. And from the results, it is clear that the coefficient of thermal expansion is significantly influenced by the aggregate type. The coefficient of thermal expansion range from about 7.8 to 12, depending on the aggregate used, while most of the coefficient of thermal expansion results fall well below the 12 as specified in the TMH7. Again, there is currently no South African standard to measure coefficient of thermal expansion of concrete, and this is an important parameter to consider in design of integral bridges, as indicated in the sensitivity analysis done by Sarah. Now going through to the drying shrinkage, and the standard that is normally specified is the SANS 5836, and that is what they typically specify in the design of integral bridges. But from the name of the code, it seems as if you can use this for concrete, but it is important to note that this standard only considers mortar and not concrete mixes. So 3 mortar specimen is required with a size of 280 by 50 by 50. And then gabbro sand and quartzite sand are used as the reference and control aggregate respectively for the fine aggregate testing. While rocks such as gabbro, norite, dolerite, and granite or quartzite is used for coarse aggregate testing, but it is also important to note that for coarse aggregate, the test sample should be crushed until the aggregate passes a sieve of nominal size 4.75 millimeters. The mix design for this standard uses cement, 1,000 grams of cement, CEM1, 600 milliliters of water, which yields a water-cement ratio of 0.6. And the mixtures containing the reference aggregate would require 4 kilograms of the reference aggregate. And then the mass of the test and control aggregate is determined as a ratio of the reference aggregate density. It is important to note that the reference and control aggregate should be prepared by combining the size fractions in the same proportion as that they occur in the fine aggregate. So these aggregates are sieved and then certain fractions are used to make up the same grading as the test aggregate. So they are not used as they are obtained from the quarry. Specimens are then cured in a water bath for 7 days. Thereafter, the specimens are removed from the curing bath and the distance between the outer ends of the anvils are measured. The specimen are then stored in a drying oven with a temperature of 50 to 55 degrees and a relative humidity of 15 to 25% for 14 days. Thereafter, the specimen are allowed to cool down to 20 to 25 degrees, and then the outer ends of the anvils are measured again, and this is done after 14 days. The drying and measuring procedure will then be repeated at 48-hour intervals until the difference between 2 successive readings does not exceed 2 micrometers per 100 millimeters of the nominal test specimen length. So typical drying shrinkage results for this standard will look like the results indicated in this graph. The gabbro was taken as the reference aggregate, ferroquartzite as the control aggregate, and basalt as the test aggregate, and then dolomite was additionally cast as a control aggregate, seeing that dolomite is excessively used in Gauteng area. From the graph, it can be seen that the reference and the control aggregates had typical drying shrinkage values of around 800 after 35 days, while the basalt aggregate had approximately 1,500 microstrain after approximately 35 days. These give unrealistic values for shrinkage. This indicates that basalt has a different drying shrinkage capacity than the other aggregates, and the results can rather be used as an aggregate comparison and not as a set value for drying shrinkage of concrete, specifically not for design purposes. And therefore, we must rather look at concrete samples and not just mortars. So the test procedure used as previously specified was not used for this setup here. We now considered concrete samples, but the same specimen size. So again, it was a 280 by 50 by 50, but the coarse and fine aggregate were used as obtained from the quarry and no additional crushing or grading was performed. The specimen were also not placed in a drying oven, but rather in a temperature and humidity controlled room, and the drying shrinkage was measured regularly up until 300 days. The drying shrinkage values again range from 800 to about 1,400, depending on the aggregate type. And again, there's a significant effect of aggregate type between the different results. But these values still are unrealistic values for shrinkage. So as previously indicated by Sarah, the specimen's shape and size will play a significant role in the drying shrinkage values obtained. And it is important to consider what specimen size as well as specimen shape should be used to determine realistic drying shrinkage values, and what test methods should be used for design purposes. I'm going to hand over again to Sarah for the conclusions.
So what we really wanted to show you today is what does change, or what is influencing integral bridge behavior, and also the variability of our concrete in South Africa made from different aggregates. You can see that definitely, obviously, the bridge environment is influencing the design, but that obviously you can, and the geographical location, which would kind of govern your temperature changes and also your relative humidity. The bridge geometry is also going to influence it. The longer it is, the more it's going to expand and contract. And then soil properties would also influence the behavior. But we focus today on the bridge material, which we predominantly are looking at concrete, reinforced concrete integral bridges. So just concluding on that, we are definitely seeing that heat of hydration needs to be controlled when concrete is being placed, especially where the cross-section varies. So that's really important to consider. It must be taken into account in terms of design and construction. And definitely something I didn't mention was also where you've got a cross-sectional variation, just differential temperature in day-night temperature variation and seasonal temperature variation also can lead to the designer requiring additional reinforcement for crack control with these stresses that develop over the change in the cross-section. We've seen that E value and alpha definitely play the value that is assumed during design can have a big impact on the load effects that are calculated, and this is now very much aggregate dependent. So when designing an integral bridge, it would be important to know where it's going to be designed or where it's going to be built, obviously, which you would, but also to know what kind of aggregate is available in that area. What should the aggregate be? And then obviously during the trial mixes, if E value and alpha value can be measured, that it would be great so that one can verify the values that were used in the design. And then to look at drying shrinkage. We see that it's difficult to measure, but our method of these little reference samples has worked really well, actually, and it's something that could be considered to in terms of looking at drying shrinkage. And we really think that concrete properties and additional concrete properties need to be measured, specifically these three that we've mentioned here, E, alpha, and drying shrinkage, and they should be looked at during the mix design and as well as during construction to make sure that one is getting the E values that were assumed in the design. As Megan has shown, the tricky thing comes in now in terms of test methods, because for all three of these, we don't actually have a good enough test method in South Africa. We've measured it obviously in different ways ourselves, but this is something we really think needs to be looked at, and for South African conditions and South African concrete test methods need to be developed for these. Lastly, just acknowledgements. Obviously, a lot of people have been part of our integral bridge research, specifically on the Van Sailspoort project. This is a SANRAL bridge, and the design team, the contractors, the concrete suppliers were really an integral part of our team when we were instrumenting that bridge. And as well as more recently, the 782 SANRAL integral bridge research team. A lot of the testing that Megan has shown today was part of that research. So I'd just like to acknowledge these groups of people. And now, we wanted to end a little bit early to allow for questions. So Billy, over to you. And if there's any questions, we're very happy to answer them.
All right. Firstly, thank you very much for the presentation, Sarah and Megan. I think we can give them a thumbs up. Where's my thumbs up? If you want to, yes, quite a few thumbs up and clapping of hands coming through. Thank you very much. Thank you for your time. Now we've got open for questions, and I see this person. I can't see who. Where is it? Grant Harley. You've got a question.
Yes, thank you very much. Thanks, Sarah. Thanks, Megan. Absolutely fascinating presentation. Really enjoyed that. Thank you. My two questions are, the first one is a bit specific and the second one more general. Did you notice any sort of ratcheting on the abutment ends due to the integral design? and the deck moving and closing over time, like settlement or anything of that sort? And then the second question is more general. Other than the temperature effects, which you found to be less than those prescribed by TMH, were there any other like major surprises with all the instrumentation and measuring that you guys did?
Thanks, Grant. Just skipping back to that pressure. So I didn't focus too much on the earth pressure here, but just to show the effect of the environment on what's happening on the bridge. And I just, this is just showing sensor 4 on the northern abutment. So that's basically that sensor down here. And you can see we got a bit of ratcheting in the first 2 seasons. But very minimal after that. So that's basically what we measured here. Obviously, that is going to be now dependent on the type of fill. So we had a sand. This was a wedge of sand that was prescribed here, and a phi value of less than 30 degrees, I think, was prescribed. Or let's just go back and check on that. So yeah, we did not see a lot of ratcheting. One of the reasons we thought possibly would affect it is the moisture content in the fill, and you've got these suctions in the fill that would kind of help the earth to stand on its own, basically, and limit that ratcheting effect, because the ratcheting is caused by the movement of the fill as the abutment is pushed into the fill and pulled away, and you've got this gap forming, and the soil can fill into that gap and then compact. So that's the mechanism causing that increase in pressure. But you can see it, some of it here, but not as much as we thought we would see more, actually. Your other question, just in terms of general interesting things, I think the heat of hydration was interesting for us, that we did not expect. Something we are, and we've, I see Jitesh is on the call, or on the meeting here, with eThekwini municipality. We've actually been monitoring 2 of their new integral bridges with a very similar cross section, and they use timber shutters instead of this was steel shutters, and we definitely are seeing less variation in heat of hydration using timber shutters and then steel shutters, as well as they specified a night pour, and this was poured in the day, and that really helped. Just, those 2 simple things really helped to limit that temperature differential between the middle of the spine beam and the flange. And then obviously I didn't also show the temperature changes within the deck. That was also something we were really interested in, what was happening in temperature. Sorry, just go to that slide there. I think the temperature is something we sort of in a jointed bridge don't really worry about, but in this integral bridge, obviously now you've got these thermal gradients causing thermal moments, and when you've got these thick and thin pieces, you've got a lot more happening in terms of temperature gradients, both vertically and to a certain extent transversely. So temperature is really being something interesting, and we've kind of dived into that topic a lot more in the lab as well now. Grant, I hope that's kind of answering you there.
Yeah, thanks so much, Sarah.
Thanks for those answers. Are there any other questions from the audience? You can type it in the chat as well if you want to. Let me just check what's in the chat. Just people's AIs being very busy. Any other questions? Maybe I can ask a question. In your experience, both of yours experience for this almost a little bit different parts of the same structure, what is the one thing you would warn people about that they must take into account that is not readily known? If that's not too a difficult question.
Sure, Billy. That's kind of a question you have to think about a little bit.
Yes.
Megan, do you want to go first?
I think Sarah mentioned one already, and it's about the temperatures. And if you actually just use wood structures or
Timber, shutter.
timber instead of the steel, you can already have a significant difference in terms of your heat of hydration, which is something I don't think everybody thinks about. So I think that's already something that she's mentioned.
Yeah, I think just two, I think, big things that we hope our guideline that is we're busy concluding now, part of our SANRAL research team, is the two big things are that concrete properties really make a big difference to your design, and just assuming the values in the code is probably not good enough, and not good. And in terms of efficient design, you're either going to be totally over designing or totally under designing. The other thing is that this deck cross section plays a huge role in your change in effective temperature, which is governing this movement of the deck basically. And we were really surprised that it wasn't as much as we thought. I mean, because looking at bridge design, you keep thinking plus and minus 25, a total temperature change of 50 degrees, but this is nowhere near that, and it's only a meter thick. If it was thicker, it was obviously going to be less. So that to me was something to think about, that you can actually, if you want to go longer, you can play around with the deck shape to go longer, because it'll change, and you're limited in terms of change in length, because obviously it's coming back to the pavement now, and you don't want the pavement behind the bridge to crack. But definitely that deck cross section is concrete, and the thicker you make it, it's got a high thermal inertia, so it doesn't change in temperature as much as one would think. And the third thing in terms of the design, which is not linked to concrete but is linked to the earth pressures that Grant was referring to, is that basically that envelope that you've got to look at is that you've got these high pressures during summer, but basically you've got zero during winter. So if you are assuming that there's earth pressure there in terms of braking forces, yes, the earth pressure won't take a lot for those braking forces, but you've got very little there. So you must look at this envelope in terms of your the lateral forces on your structure. So I think those three things are important, and I think big conclusions in our guideline that we're working on.
Excellent. Thank you very much. I'm going to go back to Grant, who had his hand up first.
Thanks. Yeah. On this slide, we're talking about minimum and maximum temperatures there, Sarah. Did you measure temperatures? I assume you did. What did you find across the deck thickness in terms of variance, and how that compares with the requirements by TMH and Eurocode? In my experience, I found that that often design, not often, but it has affected or controlled the design of the deck reinforcement, the variation across the thickness, causing bending moments rather than the longitudinal kind of direction. Did you find that those measurements were consistent with TMH?
Well, just we compared TMH's thermal gradients, both positive and negative, for the thick portion and the thin portion. We found that it was well within that range that they give, so that we didn't look at it further than that, but we definitely saw that it was nicely within the range, so that was comforting, that TMH7 gives. It is interesting that I think random thought. So that we do and in terms of getting, the other thing to note is this term effective bridge temperature. That's that weighted average temperature. So to get that, we measured 41 points across the cross section at a single point, and calculated that weighted average. So this is not obviously anything to do with the gradient. This is just that weighted average. It's going to cause the deck to push in and pull out. But the gradients looked good in terms of TMH7's requirements.
Interesting. Okay, that's great. Thanks, Sarah.
Thank you. Then we've got a question from Spamandla.
Thanks, Prof. Just a question on the alpha value that is given in the code. the 12 times 10 to the minus 6. Yeah, I was just thinking that for estimating like normal movements in the jointed bridge, that would be conservative, but for an integral bridge, using this value probably produce higher moments, probably be what's the right word, less conservative. Is that correct? Am I correct in thinking?
Well, we were seeing that the higher the alpha value that you assume in your design, you're getting higher movement and higher moment.
Oh, okay.
Yeah, but I think what we wanted to show is that if you can actually be more accurate on that alpha value, then you can have a more efficient structure. Yeah, so we were definitely seeing it, you know, it's quite a lot less than that 12. So it's not going to move as much as you think. And this is, again, you know, talking about back to Billy, what we found surprising was that, you know, when they first were building this bridge, everyone was like 90 meters. That is such a long integral bridge. But you can see the measured movement here, 10 millimeters in the year, basically.
Oh, okay.
So
Yes.
it's actually not as much as I thought. This was also, again, a surprise that, and it links very nicely with the alpha value and the change in temperature that we measured. We would, you know, have calculated that.
Okay.
Thanks, Pamandla.
Thank you.
I think we've got time for another 2 questions. I see there's one from Daniel or Daniel.
Hi, yes. Sorry, I'm sorry if maybe this has been covered in the slides that I missed. You said that the pressures were not higher than at rest, I think.
A bit higher than at rest.
Okay, how much is a bit? I'm just interested in that because normally we find that we end up trying to design for quite large coefficients to take into account that expansion. So I'm not sure if there were, how did that compare to actually the theoretical calc?
So there's the K0 value, if I'm
Yes.
reading the last slide, and then you can see the pressures above that. So at this point, we are still thinking that the way to go, that K star value that's given, and they've updated the British PD, I think it's 16994. We're still thinking that it's, you know, if you, again, measuring your not concrete, your soil properties here, and using that is probably the best way to go in terms of getting the worst case scenario pressure, but then definitely to consider zero pressure, basically very little soil. I mean, we can't prove that there was a gap forming, but there's, you know, and we could have maybe got some sort of funny pressure because of the earth pressure and side effects and that kind of thing. But we definitely are seeing that it would be prudent to design for an envelope of no pressure, and then that PD documents pressure, basically.
All right.
Thank you. And then our final question goes back to Grant.
Sorry, thanks, Grant. Sarah, did you measure mechanical strain on the main longitudinal reinforcement and correct it for any thermal strain? And if you did you find anything interesting with regards to theoretical predictions?
Your Grant, strain is tricky. We are still 10 years later trying to sort that out, because so this is our strain measurements, and we tried to be as complete as possible. So I focused on these vibrating wire strain gauges, which is measuring the strain of the concrete. And as I said in the presentation, you're measuring one strain value and it's got all the strain in it. So we were not trying to measure we're logging the one thing I didn't measure is we're logging slowly. We're logging at 15-minute intervals because we're looking at environmental effects here. So we're not trying to look at any vehicular loading. So in terms of the mechanical strain, it would be the self-weight of the structure, the parapets, the asphalt, and that kind of thing. We're not going to look at dynamic loading. On the right-hand side, we can see we actually stuck normal Wheatstone bridge strain gauges onto the rebar over here, which we've embedded in the concrete. This is something we Yuri Ardendorf, one of our PhD students, is hopefully going to be looking at, and also looking at the strain in more detail. We tried our best to get a strain profile through the deck. So we definitely are seeing, sort of hogging here and sagging there. And we also did a load test on the structure that Yuri is busy looking at in more detail. We parked a whole lot of trucks, try to get worst case sagging and worst case hogging on Pier B, I think. And that's something we are looking at. So yeah, watch the space, because we've looked at it sort of superficially. Now we want to dive deep into these strain values. Sorry, Pier E, I think, it's not Pier B. But yeah, at this point, we're seeing definitely shrinkage on the strain values. We can definitely pick up shrinkage if you take out the temperature effects. And you can definitely see less shrinkage in the beams and more shrinkage in the flanges. So that differential shrinkage, which can cause cracking. And again, you want to beef up your longitudinal steel to handle that thickness differential in terms of differential shrinkage and differential temperature. But in terms of the mechanical strain and looking at that load test, we're busy still analyzing that data.
Thanks so much.
Thanks. I think we should start wrapping up. Thank you very much to our two presenters again, Megan and Sarah. Thank you for taking the time and preparing and presenting and answering the questions very well as well. Thank you very much. And for the audience, for those of you, this was an overload of information. You've got luckily a long weekend ahead to try and relax and get your brain back to your work on next week. So thank you all for attending. I really appreciate it. I will just urge you again, if you're not a member, become a member of the Concrete Society. We'll continue bringing you this kind of presentations. And thank you very much, and have a lovely evening further. Thanks.